Did everybody get one? I just tried to lay one on your desk. So this section is actually real short, and mostly what you're doing is learning how to use your calculator and do what we call a regression equation. And you have to have your calculator to do that. You learn how to do that in a statistics class. In the modern world, you know, nobody does regression equations by hand anymore because it's incredibly tedious. So you're lucky you've got a graphing calculator that's going to do that for you automatically. So what we're going to get into a little bit here is the idea of what a linear regression is. And really what we're going to look at is what a mathematical model is. And that's the big thing that you might study in business and economics is we have data and we analyze it. Okay, that's what you do. And a mathematical model is what you try to come up with because it will give you a tool that'll help you analyze whatever that situation is, right? So what you're always going to try to do is when you're constructing a mathematical model, you're just trying to come up with a function or an equation that models whatever thing that you're interested in doing. Now, what we're going to focus on mostly in this section is what we call a linear model. That's what we've been talking about. So we know y equals mx plus b. Okay, that's the line, the equation of a line. Okay, so a couple of examples on this. We've learned the m is the slope, b is the y-intercept. We've learned that b is a fixed quantity and m is a rate of change. Okay, those are the key things. Now, pay attention to what we have here. One of the things I want you to be able to do as a student is to recognize when you have a linear relation. I'm going to kind of teach you that first. So this is kind of what happens if it's linear. Yeah.
Just really quick.
Yeah.
This is like on like the third page, fourth page back.
What's that?
Our first page is page 4.
Is it all messed up?
Yeah.
Is everything there though?
Yeah, it's there.
Okay. Maybe when I stuck it in the copy machine, I had the wrong order. So, okay. So I'll try to be aware of that when I do that then. Okay. When I go over things. Okay. So on this page right here, what it says is if x changes at a constant rate, then y also changes at a constant rate. That's what it means for something to be linear. Okay. Now let me show you what I mean by this. And this is what I want to try to start you off on this. The x values are going up 1, right? Just write a note to yourself that that's going up 1. Now, look at the y's. Are they going up at a constant rate? $1, $1.30, $1.60? Yeah, they're doing what? They're going up by 30 cents. Good, okay? So you want to write yourself a note on that. I know that's linear because as x goes up 1, the y goes up 30. They both go up at a constant rate. They don't have to be the same rate, but that's how you know. And of course, what happens is if you plotted those points, then you would have a line. Okay, so that's what the idea is. A lot of times students understand the line part, but not the idea of the constant rate of change. So let's go to the next page, which I guess is somewhere in your packet, right? Okay, is that the next page? Or page 2, right? Okay, so with this one, what we're going to do is I've got 2 tables of values here, and we're going to kind of look and compare these 2 tables of values right here. So let's look at this right here. This one is, you're doing what? You're going up 2. What's happening on the y? You're going up 6. Okay, so this is a linear relation. Okay, that's what that is. Now, when I'm talking about a constant rate of change, it would look like this. So what we're going to do is we're just going to find a slope. I want you to write this down because this is something I want you to see. So let's take like just these 2 points right here. Just keep it simple and find the slope between those 2 points. If you were finding the slope between these 2 points, you would do 6 minus 0 over 2 minus 0. That would give 6 over 2, so that's equal to 3. Okay, so your rate of change is 3. Okay, and what that really means is that's 3 over 1, so it means every time the time goes up 1, the distance goes up 3. Okay, that's what that means. And now let's put these 2 together. Let's find the slope of these 2 and see if it's the same. So if I did this, I would go 18 minus 12 over 6 minus 4. That would end up being 6 over 2, so see it's still 3. So what you have is you have a constant rate of change. That's what a linear function is. So it's measuring something that's changing at the same rate always. Does that make sense? Now, a lot of you are going to take like business calculus, and the talking about how things are changing becomes really the big deal that what you're learning in here. So things are changing the same. Now I want you to look at the next table. Does that look like it would be linear? Okay, I've seen some people go like this and then like this. What do you think? Yeah, it's no. What's the difference? Y isn't going up at a constant rate, right? Now what's happening on this, yeah, you're going up 1 there, but look at this. You're going up 3, you're going up 5, you're going up 7. Now there's a pattern to that, but it keeps changing. Okay, so it's not the same. So this one right here is non-linear. Okay, so that table would show that's not nonlinear. If you graphed those points, they wouldn't make a line. They would make more like a curve, okay, like that. Okay, all right. So let's go through and let's look at this next one. What I want you all to do down here is look at each of these 3 tables and just write in the blank below whether if you think it's linear or nonlinear. You can do that in your head too. Okay, so just see if you got that put together. Just means if x goes up at a constant rate, so does y. That's all you look for. Okay, some of these are probably linear and some of them are probably nonlinear. So what do you think about the first one? Nonlinear. Okay, yeah, that's nonlinear. Okay, and that's going up 1 is what that's doing. This is changing. That's going like down 5, down 3, down 1. Okay, how about the next one? That's pretty easy to see that's linear, right? You go up 1, go up 1. That one's linear. Okay, how about the next one? Yep, that's linear. This goes up 1. This goes up by what? A quarter, 25 cents. So that's linear. So if you plotted the points on C, it would make a line. That's the idea. So that's what we mean by data being linear. It has a constant rate of change. All right. Okay, so on here, this is just kind of a couple of things that we've already talked about. A slope is a real big deal in this class and in calculus, so it's giving you a rate of change. All right, when you have x as those 2 points. So the rise is the change of the y-coordinate like we've talked about, and the run is the change of the x-coordinate. Okay, that's it. All right, now let's go to page 3. And we're going to put together, what we're trying to do in here is get comfortable with the idea of a linear model. And the hard part of this usually for students is building it. Okay, you're given some piece of information and you're trying to build it, so you're trying to build an equation on this. Okay. So this is something, okay, like when I go to the doctor, a lot of times they have this chart, and you can look at your height and what your ideal body weight would be, okay? My doctor sometimes will say you need to lose 5 pounds or 10 pounds or something like that, and that relationship is usually linear. It just means the taller you are, okay, the more your weight can be to make you an ideal, but it tends to go in a linear fashion, okay, which makes sense to me. It's like I'm like 5'6" or something like that, and I have a body weight maybe of 160. Somebody 6 feet, that they don't have to have a body weight of 500. It goes linear at kind of that same slope. Does that make sense to you? Okay. So the idea with this one, it says a physician found that the ideal body weight of a woman was 49 kilograms. That's like fixed. And then 1.7 kilograms for every inch that you're over 5 foot. So that means so the ideal body weight, according to this physician, would be 49 to start with, regardless, okay? They're just assuming that you're talking about people over 5 foot. That's what they're assuming. Then every time you add an inch to 5, well, it would just be another 1.7. Does that make sense to you? Okay. So if you're going to put this in a linear model, it'd kind of be like this. Something is always fixed on a linear model. What is fixed in this problem?
5 feet.
The 49. The 49 is, okay, if we're going to calculate your ideal body weight, we're going to start with 49, right? Okay, so the fixed is going to be the 49 kilograms. Okay, what is varying in this? What's the variable change? See, that's the slope. So the slope is like the variable change. So it kind of goes like this. And you'll get used to this, because we're going to do this throughout the semester. Let's just write down y equals mx plus b. Okay, that's what we know the model is going to be because it's linear. Okay, so the fixed one is the b. That's the 49. That's fixed. That's where we start. And what you would expect if you graphed this, you would start at a y-intercept of 49, then the body weight would increase. Does that make sense? Okay, so your variable on this would just be, and what you would have on that is you would have, that would be 5. Well, that variation is every time you add an inch over 5, then it's going to be 1.7 kilograms more. So what that x is representing is it's just representing inches over 5 foot. Does that make any sense? Okay, that's usually the hardest part of the problem is getting this model built. So your model is going to go like this. Now they tell you what variables you want to use. I think they say W is your body weight. So you're going to have, instead of y, you're going to have w, because that's what we're finding. And then they say for inches, do they give another variable on that, or am I missing something? I guess we'll just leave that as x. So that will be 1.7x plus 49. Okay, so that is the linear model on that. And again, what it's saying is, if you're 5 foot, what's your ideal body weight? 49. That's the beginning. And then if you're 5'1", it's going to be 49 plus 1.7 times 1 inch. Okay, like that. So that's what it's going to be, and it's going to go up at a constant rate of change. Okay, so that is your mathematical model. Now, we're going to interpret. One thing you'll do a lot in this class is we're trying to make sure we understand the meaning of stuff. Okay, the slope is 1.7. Now, I want you to be able, when I want you to interpret, I want you to really tell that you understand this. So I would write on my paper 1.7 over 1, and that's a rise, and that is also, that's given a weight. Okay, remember y is weight on here. This is given a run, and then what that is that's inches. Okay, and then this is the way that I want you to interpret this. You'll do this all semester. It really means this. Every time you add an inch to your height, what happens? Your ideal weight goes up 1.7. It's every time that happens, that happens. Okay, so the way I would like you to think about interpreting this is just write exactly what I said. So just write down for every inch, the ideal weight changes by, and it goes up by, you can just say it changes by 1.7 kilograms. Okay? So if you get a slope's a rise over run. The rise is how the y values are changing. The run is that. Okay? And put it over 1, and then you can tell me what that means. Okay? Does that make sense? Okay? All right. Now, let's look at this next. The rest of this is just kind of a little bit of number crunching. Okay, so with part C, it says, if a woman is 5'4", what would her ideal body weight be? Then what do? You take the model and do what? Remember, it's past 4. How far past 5 feet are you? 4 inches. Good. So what you'll do is you'll do W equals 1.7 times 4 plus 49. Okay, now you're plugging in for x, however many inches you are past 5 feet. So then we can take the calculator and go and work it out. So I got 1.7 and then times 4 and then plus 49. Okay, so that's going to be 55.8 kilograms would be that person's ideal weight. Okay, does that make sense? Okay, so it's inches past 5 feet. That's how that goes. Okay, let's read the next one. So it says, if a woman is 60 kilograms, what does the model predict about her height? Okay, so basically we got the model. The model, again, is 1.7x plus 49. Okay, what are you going to do with the 60? Where does it go? That's a weight, right? So you're going to put the 60 in there, and you're going to have an equation that you have to solve for x. And that x is going to be inches, okay? So what we'll have is we'll have 60 equals 1.7x plus 49, and then we can crunch out the equation. So now it's just a basic linear equation, so that's going to be, what's that, 11 equals 1.7x. Divide by 1.7, we may have to round that a little bit, and I'll do that on the calculator. Let's see what we get here. So 11 divided by 1.7 is going to give about 6.4. So I'm going to say x is about, let's say about 6.5. Okay, so how tall is this woman? Is she 6.5 or 5'6"? Yeah, she's 5'6". Okay, so really the answer would be 5 foot and about 6.5 inches, or feet. I'm sorry, like that. Okay, that's it. Yeah.
This was on my math lab, but you put 5'7" or 5'6"?
Well, if they want, sometimes it depends on what they say. They might even say
round to the nearest integer.
The 10th. If it say round to the nearest whole number, then this would be 6. Okay, because then you'd be looking at 6.4. That's the 0.4 is under 5, so you would change it to 6. So if they said round to the nearest inch, it would be 5'6". Okay, like that. Okay. Okay. Does everybody have anybody have a question about that? Is that okay? How that went? Okay. Everything we do in here is talking about linear models. So let's find wherever this is on your handout. So how does it go? Just in a totally backwards order? Or is it all? Oh, okay. All right. Well, we'll get them all done. And you can rearrange it if you want to, but you can leave it this way too. All right. So with this one, it's kind of the same thing. Now, what we do a lot of times in statistics is, we collect data. All right. So what we have is what this is saying is as the year changes, then the production percent of fossil fuels is changing. Okay. What's happening to, what are we trying to do in the world with fossil fuels? We want them to go down, right? Okay. Oil isn't forever. So what's happening is the trend is towards more renewables and so forth. So it might be that this is some sort of a linear model that we have, right? So we're going to put this together. They've already given you the linear model this time, so it becomes just a matter of interpretation based on this chart. So what I'm seeing is as time goes further and further into the future, the trend is the production is going down, right? Okay. So what we're going to do is we're going to do a scatter plot. The first thing is a scatter plot. Now, if I ask you to do a scatter plot, that just means plot the points. So what I want you to do is in this area here, just go ahead and draw yourself out an axis. And then again, what we want to do is we want to get this kind of labeled and everything. Okay, so this is going to be the year. And it says since 1985. So we're going to write down the year since 1985. Okay, you want to write that down. That's what X is. And then Y is going to be, that is the production. So that's going to be Y, and then we just put on here is the production. You just abbreviate this as a percentage like that. Now all we do is we just plot points, okay? Now we're going to see if it makes a line or not. So I'm going to zoom out on this a little bit so I can see what I'm doing. Okay, so just do it like this. You can go ahead. This is something that you see a lot of times done in graphs and, in the real world in business. We're not starting at 0. We're starting, well, actually we are, now that I think of it. We're going to start at 0, and then we're just going to go 5, 10, 15, 20, 25, because that's what the problem said, is it says that's years past 1985. Okay, so we'll just do 0 and then just scale it. 5, 10, 15, 20, and 25. Okay, like that and so forth like that. And then all we're going to do on this, the production. Now, one thing that you can do on this is, and sometimes I'll see students do things that are unnecessary. You don't want to go like, you don't want to just start at like 70. You don't want to do that. What you can do is you can either just kind of go 10, 20, 30, and so forth like that. You can do that if you want to, or you can do this. Okay, I don't mind if you do this because this is kind of a common practice, is you can put like a little squiggly line there. And then you decide where you want to start it. Let's just start it at like 70, because that's the low. Is that? Yeah, let's start it at 70, and then we can go like 80 and maybe up to 90 or something like that. Okay, and that's good enough. Okay, you can do that. Just if you need to start your graph a little bit differently like that. Now all you're doing is you're just putting dots. So the first one would be 1985. That would be year 0. And then the production's 85, so you simply put a dot there. And that's all you do. You go to 1990. The next one, the production is 83. Just estimate. And then the next one is 81. Let's see, the next one is 80. I think I'm getting that right. And then the next one would be, what, 79? And then 78. And I guess you'd want to go all the way up to 30. And then that one kind of jumps back up a little bit, jumps up a little bit to 80 like that. So that's what we mean by a scatter plot. You don't connect the dots into a line or anything, but you look at that. Now that kind of makes a line, doesn't it? It's not a perfect line, and that's the way the real world works, is hardly anything's perfect, but it's a trend. So we can come up with a model, which is what you're given here, that can make predictions about the data. Okay, and that's what you do a lot when you're dealing with statistics. Okay, all right. So that's a scatter plot. That's what you're doing with this. Now the slope in your mathematical model, the slope is negative 0.19 is what that is. Now do exactly like we do in the last problem. If you're going to interpret this, just put it over 1 and think about what this means. It's a rise over run. Okay, so first of all, the 0.19, what does that 0.19 mean? What's happening? The line's going down, right? Okay, that's why it's a negative slope, but what is the meaning of that 0.19? That's a change in the y, isn't it? So you're going down like that. What's the meaning of 1? That's 1 year, okay? So every time a year goes up, what happens to the production percentage? It goes down about 0.19. Okay, that's how that goes. So one way to write this interpretation on this would be like this. You would say, as the year goes up 1, and there's a lot of ways to write this, but this is a good way to think through it. As the year goes up 1, then production, and a good way to write this is just say then production decreases, since it's going down, by 0.19. Okay, and that would be roughly like a percent like that. So that's what that means. So if you have a slope, you want to know what it means. You don't want to know it's just the slope, or it's a rate of change. You want to know how it relates to the variables in the model. That's the idea. All right, everybody with me there? Okay. Always put the slope over 1 and talk out. As that goes up 1, that goes down, or goes down 0.19 and relate it to the variables. That's the idea. Okay. So what we're going to do is see what happens in 2025. All right, so we started in 1985, and we're going up to 2025. So you need to find out how far apart that is. So I think that's like, what, 40, I think? Okay, if you subtract those two numbers, if you do 2025 minus 1985, then that's going to be 40. Okay, so what you do is take the mathematical model that I gave you and just replace the x with 40. So what we'll do is we'll do y equals negative 0.19 times 40, and then plus 83.75, and you can do it on your calculator, and then that would predict where it is. Okay, so it would go along with this trend then. Okay, all right, so let me crunch that out. Negative 0.19 and times 40, and let's see, plus 83.75. Let's see what comes out. Okay, so that's about that. Is that right? Oh yeah, 3.5. That makes no sense whatsoever. Okay. Okay, 83.75 is what it would be. Thank you.
You actually did 19 instead of 1.
What did I do now? Ah, okay. I might just say, students, what did you get?
76.15.
I have to click like my mouse every time I do this on here, so it's a little tedious. Okay, tell me if I'm on the right track. Now. I like that answer. That's logical. Okay, good. So that would be about 76.15% like that. Okay, so that's the idea. Okay, So that's a mathematical model, as we can make predictions about it, okay? All right? So, like, if you've ever wondered, like, you'll read stuff like, okay, we think the population of the Earth is going to be 10 billion people in 30 years. How did they figure that out? Well, they look at data, and they see if there's a mathematical model that fits that data to make predictions. It's not perfect, because there's all kinds of things that can happen, but that's what we do with data, is we try to make a model that can make predictions then. Okay, the next thing on this one just says use the model to estimate the first year for which the fuel production is less than 70% of the total energy production. Okay, well, okay, let's write down our model. If you got a model, write it down. So the model is y equals, again, negative 0.19x, and then plus 83.75. So what are you going to do this time? Are you finding x or y in this problem? That's the key question.
Suppose 70%.
That goes in. Where does the 70% go in? For y, right. X is the number of years. So you've got to be clear on what the variables are. So just put 70. Don't worry about a decimal. Just do 70. And then negative 0.19x plus 83.75. Okay, like that. And then you solve that equation. So you're doing that backwards. So now it's just a basic equation. You're going to subtract 83.75. Okay, and I'll do that on the calculator, and we'll see what that is now. Okay, so 70 minus 83.75, and that will give me negative 13.75 equals negative 0.19x, and then I can divide both sides by the negative 0.19. Okay, just do that one step on my calculator. Okay, so what we got on that is x. Did I do that right? That sounds kind of weird, but I mean, that's just way off in the future, but it could certainly be that way. It's kind of logical now that I think of it. So about 72.4. Okay, now if I wanted you to tell me what year that's going to happen, what would you do? When did time begin according to this problem? 1985, thank you. Okay, all right. So what we'd do is we'd do 1985, and let's just do plus 72. Okay, let's do that. So if you do that, that would be 715. So that would be in the year 2057. That's what we'd expect. Okay, that's how that goes. All right, so if you've got a linear model, you can kind of work with it both ways. Okay, all right? All right, is that okay? Thumbs up, thumbs down, thumbs sideways? All right, okay. Now, I already gave you the model on that, so it's more interpretation is what we're trying to learn, okay? Okay, now, what we're going to do now is kind of get into the calculator. So get your calculator out. If you didn't bring one, just kind of, you need to probably start bringing one, because I'm going to start doing this stuff. Every class we're going to be using it a lot. So these are two examples of linear regression, okay? And where you have a line. So what happens is, and when you start collecting data, is it generally makes a line. Okay, it's not perfect, but it's kind of the data is kind of scattered. So a lot of things in our world follow a linear model, and that getting that model can be done with what's called regression analysis, and it's real tedious. Well, you learn that in statistics classes, but it's so tedious now most of the time we just let the computer take over because it's a big arithmetic problem with a lot of number crunching. So these are the steps. I've done this for you, so when you're doing this and learning how to do this, you can refer to this. Now what I'm going to do is have you go to the next page and then get your calculator out, and then we'll kind of go through this together. And if I lose you or something, just slow me down, okay? So because it'll take a little bit of time to show how to do this. So what we're going to do, yeah, go ahead. What's that? Yeah, you need a graphing calculator for this class. And you can go to, if you want to rent one, you can go to Student Services at CCD, and you can rent one for one semester. I don't know how much it costs, but that's another possibility. But this what I'm showing you now, there's no way you can do this unless you have a graphing calculator. So yeah, okay, so you need to figure out how you're going to get one, okay? All right, so what we're going to do with this one, we're going to make a scatter plot, then I'm going to teach you the stuff on the calculator here. Okay, so with this one, and my computer's frozen again. There it goes. Okay, so okay, let's do it. We're going to do a scatter plot for average annual temperature. So what we're going to do is take a look at that data right there. Okay, so you're going to do a lot of scatter plots kind of in this class from time to time, and I'm going to show you how to do a scatter plot on your calculator too. All right, so what we want to do on this, we can start with 1965. And what I'm going to do on this is, let's do this like this. This is kind of a good way to do this, is kind of put that little squiggly line and then just start at 1965. Okay, and actually let's start that at 0, and then we'll say years past 1965. Let's do it that way. You can do it either way, but it's probably better if you do it this way. So let's label this as years past 1965. Okay, and then this is going to be average, you can abbreviate anything you want to, average annual temperature. And yeah, you would want to put Fahrenheit there because that's pretty important. Okay, so what we're going to do with this then is, I think it would be logical, since the temperatures are all in the 50s. A lot of times I'll see students give me a graph and they're going like they're not doing anything with decimals. So if you want to make it kind of expanded a little bit, I would suggest that you do something kind of like this. I'd do that little squiggly line, and then it looks like the lowest temperature is above 51. So a good way to do this might be to do something like 51, I'm just trying to come up with something that's logical, 52, 53, 54, 55. Okay, that's pretty logical. Okay, and that way you can just kind of expand your graph out a little bit. And then as far as the years go, then we're going by 10 years. So we could go 10, 20, and just every 10 years like that, and so forth. Okay, then again, all you're doing on this, on a scatter plot, you're simply plotting data. So in the first year, you're at about 51.6, so it's a little more than half. The next one is about 51.5, so it's right at the halfway point. And then the next one, you're at 51.3, so it's going down a little bit. Then the next one jumps up to 52.6, I think, and then 53, and then 54.4. So I'm just kind of approximating that. Okay, so that's plotting points. Does that make a line? Kind of ish? Yeah, sort of. Okay. It kind of jumps around. It's not perfect, but it looks like it might make a line. Okay, now here's what we're going to do on the calculator. And this may be new to a lot of you, so just if you forget the keystrokes, refer to the notes that I gave you. So what you want to do first of all, if you brought your calculator, step 1 is find your stat key. So you'll have a stat key, and you want to press that stat key. All right. Now you want to press, it's going to highlight enter, so go ahead and press enter, and then I want everybody to carefully tell me what's on their calculator. Okay, what you should see is a bunch of lists, L1, L2, L3, and so forth in that order. Does everybody see that? Or is there anything different? Have you got something different?
No, what did you press?
Okay, what I did again is I did stat, and I did edit like that, and just press enter. Because what you got to do is you got to make sure you're ready to put a list in your calculator. Has everybody got that okay? All right. Every now and then students will borrow a calculator from a friend and it's all screwed up. That's why I'm asking. Okay, and I got to show them how to fix it. Okay. So what you're going to do is you put data in like this. Now what you're going to do is, since we're not going to do 1965, we're going to do 0. So just type in these years. Just go straight down. 0, press enter. 10, go all the way down like we did. Just go down to 50. So it's going to be 10, 20, and so forth like that. Just get your X values in. Okay, so that'll take care of that. Okay, now go back. Now just use your cursor key. Now put everything in L2. So L2, just put the numbers in. We have 51.69 and so forth. 51.5. And let's see, we're at 51.3. 52.65. And 53.64. And 54.4. You're a lot faster than I am. It takes sometimes a little more time to put that in your calculator. All right, everybody with me? Okay. Now let me show you how to do a scatter plot on your graphing calculator. Okay. The first thing that you want to do is you want to set your window. Okay, and we're going to set the window just like what we drew on paper. So just go like this. We're just going to go press window. And we're going to go 0 to 50. So for X minimum, go 0. X maximum, put 50. Scale by 10. Like that. Right? Now, what we're going to do on this, we can't really do the little squiggly thing on this. We're just going to have to start for Y. We're going to have to start at 0. And then what we're going to do is probably go up to 55. So we can go like 0 to 55. And then scale it maybe by 5. Okay, would be logical to me. Okay, like that. All right, now what will happen on this is the next thing that you got to kind of do on here is do this. Now, here's the easiest way to get your scatter plot to come out. So has everybody got their data in and with me where I am? Okay, so now press your Y equals button. And if you have graphs, so we did this earlier in the class, go ahead and take those things out. You want to get those things out of there. We don't want those to graph. What you do is this, okay? Take your up cursor key and get it blinking on plot 1. Then press enter. Just move that cursor up to plot 1 and press enter. Okay, now what that's going to do is that's going to allow a scatter plot to come out. One of the things you're going to have to learn in this class is if you want a scatter plot to come out, that has to be highlighted. If you want just an equation to come out, it needs to be unhighlighted. Okay, is everybody with me? Yeah, okay, press graph and see what happens. Okay, it may look a little bit different than mine, but it's a scatter plot. Okay, you should have, you may have little different things on there. You may have like little plus signs or something like that, but that's how you do the scatter plot. All right, everybody follow me okay and keep up? Okay, so that's how you can do a scatter plot is like that. Okay, you can do one by hand and do that. Okay, now I'm going to teach you how to do the regression equation. All right, so what we want to do, go ahead and let's do this. I'll kind of write down the keystrokes as we go, and you don't have to because it's on the previous page. So what you want to do is you want to start by pressing your stat button, like this. Okay, then you want to go over, move over to where it says calc. You're going to do regression equations throughout the semester, so you want to be solid. Go down to option 4, where it says linear regression. Now, there's 2 linear regressions. That's the one you're familiar with, y equals mx plus b. It just says ax plus b. That's the same thing except backwards. So just use that option number 4 like that, and then press enter. And I'll show you what happens. So now press enter. And then out will come what you want. Now, it'll look different on different calculators. What you typically have is you put x in L1, you put x in L2. All right, and then you just go down to where it says calculate, and then you press enter. But you want to make sure L1 and L2 comes up as the default. So now just press enter, and then it'll find that line for you. Okay, so that means the answer to the problem is y equals, let's use like 4 decimals. So what I'm getting on here is 0.0609. Let's just write that. Let's write it as 0609x, and then plus 51.0071 like that. So that's the mathematical model. If you did that by hand, we'd be working on it the rest of the day. I'm not kidding. I mean, it's like a real tedious, and people used to have to do this without calculators. It took forever. Okay, so that's how that works out. Did that work for everybody okay? Okay, all right, now I want you to do one more thing. So what I want you to do on this is go to y equals, all right, and I'll go ahead and put that answer we got in your calculator. So just go to y1 and do 0.0609, and then X, and then the plus 51.0071. All right, and then just press graph. All right, so once you get that put in, press graph, and look what happens. What did it do? It made what we call a line of best fit. So that actually is, it turns out that line is the best way to get those dots close to that line. Okay, that's called a linear regression equation. And now that you have that, you can make predictions and answer questions about whatever situation we're looking at. All right, is that working okay? Okay, so that's a regression equation. All right, so we're going to do one more thing with this. So this says, based on the linear regression model, predict the average temperature in 2025. Okay, so remember, I think we started at, what year did we start at on this? 1965. So what you would do with this is 2025 minus 1965. Okay, so that's what, 35, 45, 55, that's what, 60 years? No, not 6, yeah? Is that 60? I'm trying to do that in my head. Yeah, that's right, isn't it? Okay. All right, so what we do is we just go y equals 0.0609 times 60 plus 51.0071. Okay. Now, so what I'm going to do with this then is just do this on the calculator, and then that'll give us a prediction of what that temperature is. So 0.0609 times 51.0071, and let's see if this is logical. I did something wrong again. What in the heck did I do? That's good that I'm showing that, though, because sometimes students do like I'm doing and putting the wrong stuff in their calculator, and they don't catch that it's not making sense. So what I'm trying to do is I'm trying to get a temperature out of this. So the temperature needs to be logical. Okay, does that look right? Okay, is that right? Is that what you guys got? Okay, you can do it twice as fast on your calculator than I can on this one. So it would be about 54, we'll just say 7 degrees. Okay, like that, 54.7 degrees. Okay, that would be the idea. All right. Okay, so what I want you to do is, and I want you to do this at home outside of class. I do want this last page filled out. I want you to just do this on your calculator. And at the beginning of class, I'll just put up the answers. But please try to do that and make sure that you know how to do regression equations, okay? And if you don't have a calculator, you need to be getting one. And student services, I don't know where their office is. I think it's in Tivoli for CCD. They'll rent calculators and do that. And by the way, if you go to Confluence right now, there's free food. Did you know that? It's about over. You got 10 minutes to get a free hamburger, I think, because I do have a free hamburger over there. I think it ends in 2. So, and student services is over in Confluence right now at that thing that we have outside the building, and they can talk to you about covers. You too. Thank you. Okay, Labor Day weekend too. Enjoy. Don't forget about your math.
Oh yeah, we don't have school Monday, right?
What's that? No school Monday.
Okay.
Yay, and it's the only holiday we get until Thanksgiving. So enjoy. Take care.
My
Yep.
graph is kind of weird. Like it shows
Sure.
this little.
Okay, you've got what's called a stem and leaf plot. Okay, let me take a look then.
Those things are weird. Those things are super weird.
Okay, you got maybe 2 things on. Okay, so let me show you. You won't ever have to do this. I went stat plot. If I go second stat plot, it opens this up. The only one that needs to be on is the scatter plot. So see that little thing there? That's what's coming out. I'm going to go over here, press enter, and I'm going to turn that off. Okay. All right. Then if I do this, let's see. There we go.
Oh, sweet.
See what happens? A lot of times you have a calculator from a friend or something, and
Yeah.
they're in a stats class, and it's all jacked up. So now you're good. Okay.
Thank you.
I hate that. When I took AP Stats, it confused
Yeah,
me.
if you do stats, you learn a ton of stuff on your calculator.
Right one.
It is.
Okay.
Yeah, so all you should
I
have to
haven't
do
opened
is,
it yet 'cause I was
oh, okay.
scared. No, you
Okay.
can open it. I
And
just-
you do get a 28-day free trial. So if you've got it and you paid for it, you might as well go ahead and put it in.
Okay.
You'll be good. Okay?
Thank you.
All right.